go ahead and begin. So I guess start with questions. So everybody has the study guide. The final's Wednesday at 8 o'clock here. So just go over chapter 9. So probably won't take you more than an hour to do. Bring a calculator. Any other questions? Okay. So let me collect your assignment then. If you haven't already emailed it, yeah, email is fine. I would take a picture, or just email it. Email it. Okay, just email it later. Assignments folder very first file. Okay, so this chapter is all about tissue and stresses and strains on tissue. What was the formula to calculate stress? So tensile stress, compressive stress, shear stress, what formula do we have? So you have a force, and then that force is distributed over a certain area. So, hey Logan. So mathematically, a given amount of force that is applied over a smaller area means more stress. So the more a force is distributed over a larger area, that would be lesser stress. So in terms of injury prevention, distributing force over larger area lessens the risk for injury. So injury can happen with lots of force applied all at once, or it can happen more in overuse injuries with smaller amounts of force that's applied repeatedly without sufficient recovery. So the time for recovery is really important to allow tissues to rebuild and be stronger than they were to begin with. If we look at just the amount of force muscles have to produce to keep our spine stable. So sometimes spinal stability is equated with core stability. So just picking up a relatively small box, you look at the pivot point in our low back. We'll say the pivot point is the junction between the fifth lumbar vertebrae and the first sacral vertebrae. So this would be considered our axis, this dot right there. That's the joint center. And so everything on one side of the axis represents resistive torque. So do you remember what two components comprise torque? Remember from our discussion on torque, how do we calculate it? You have a force, but what else is important besides the force? The distance from the axis, right? What do we call that distance, the perpendicular distance from the axis to where the force is being applied? Yeah, we call that the moment arm. So in this diagram, you have several different resistive torques. Notice that resistive torque can come from the weight of body segments, but it can also come from any additional resistance that we're holding in the hands. So in this case, we have 1, 2, 3, 4 different components that contribute to resistive torque. So we have the box, and it has a certain distance from from this axis in the spine. And then we have the weight of the arms, and we have the weight of the trunk. And so all of these things have a certain distance, the weight of the head from that axis. So all of those things contribute resistive torque. And so we have to have our spinal extensor muscles oppose that resistive torque. So remember our discussion about muscular torque versus resistive torque? Okay, so in order to hold something like a box, the muscular torque has to equal the resistive torque. So what I like about this illustration is it shows the actual amount of distance that the muscle has to work with. So if we say this is the distal attachment of maybe one of the erector spinae muscles. So it's kind of a simplified version because how many erector spinae muscles do we have in that group? Sometimes called the sacrospinalis group. And if you remember from anatomy, we have three of those. So the spinalis and longissimus and iliocostalis. So if we simplify and say, okay, well this represents one of those muscles, it only has 6 centimeters to work with. So this would be the moment arm for the muscle right here. So you have all of this resistive torque on this side of the axis, and then on the opposite side, the muscles have just that 6 centimeters to work with. So what are the implications of that for a muscle? Given that the moment arm is very small, how are we able to get sufficient muscular torque? Has to be a lot of force. Is it any wonder that 4 out of every 5 people will have low back problems at some point in their life? Because these muscles have a huge role in resisting all of that torque. So how many of you have ever had a job where you have to repeatedly lift boxes all day long? Yeah, so now you get kind of an appreciation for what those muscles go through. So at the end of an 8 or a 12-hour shift, those muscles maybe aren't the same as when you started. They start to get fatigued and tired. So those muscles are not activating properly, and then all of a sudden it's ligaments that are taking on that stabilizing role versus muscles. So muscles have to take on the lion's share of stabilizing functions because those facet articulations and ligaments, other passive tissues like discs, really have a limited capacity to oppose all of this resistive torque. So that's why strengthening those muscles is a #1 priority. It's really not about maximal strength so much. It's more about muscle endurance. So if you're repeatedly required to do things where you're lifting for several hours at a time, like in an occupational setting, those muscles have to have a lot of fatigue resistance. So it's more about muscle endurance. It's not about necessarily dynamic actions, like on your final exam. It's more about isometric actions. So the ability of those erector spinae muscles to isometrically fix the spine and the lumbopelvic complex in a position where most of the movement comes around the hips. How many of you have ever heard that? Lift with your hips. Everything around the middle here is static, it's isometric, it's stable. Okay, so you got to read a nice article here about squats, and there's lots of evidence on squats and deep squats and hearing different perspectives on that issue. I really enjoyed the biomechanics of the article. We talk about osteokinematic motions as part of kinesiology. So osteokinematic motions are large motions of limbs, like flexion, extension, abduction, adduction, internal and external rotation. But we also have to consider the smaller actions that take place between articulating bones. So if we look at just a simple movement where you are squatting down, that involves flexion of the knee joint, and then standing back up, that involves extension of the knee joint. So flexion and extension, those are osteokinematic motions. But if we look at what's happening within the bones that make up the knee joint articulation, we have the femur and we have the tibia. So the knee joint is sometimes called the tibiofemoral joint. And as we flex that joint, as we begin our descent into a squat, what we have are two things that happen. We have a posterior rolling of the femoral condyles on the tibial plateau, but we also have this anterior sliding that takes place. So the two major arthrokinematic motions are roll and slide. Roll and slide. So, question, what keeps the femur from just rolling right off the tibia? Right off the cliff there. What keeps that from? Doesn't happen. What? Yes. Say that louder.
Your ACL.
Yes. So you have ligaments that keep these arthrokinematic motions in check. The anterior cruciate ligament, the posterior cruciate ligament, the medial and lateral, collateral ligaments. We also have to consider that there's a little bit of rotation between the femur and tibia. But roll and slide are the primary arthrokinematic motions. So then in standing back up, it's exactly the opposite. So we have an anterior rolling and a posterior sliding. So there's friction between articulating surfaces. What type of tissue do we have at the ends of long bones that minimizes friction during these types of actions? Yeah, hyaline, sometimes called articular cartilage. So that's a really super type of tissue, just a few millimeters in thickness, but it acts a lot like a water-filled sponge. So during weight bearing, all of the water, or in this case, it's interstitial fluid, is squeezed out, and then during unloading, like you're in a seated position, all of that interstitial fluid goes back into the cartilage, so it increases in thickness. So why is that efflux and influx of interstitial fluid important for cartilage specifically? What is it about cartilage that's maybe a little bit different from other tissues? Yeah, it's avascular. So it has to have that nutrients, oxygen and glucose, supplied by the movement of interstitial fluid. So movement is a good thing for cartilage because that promotes nutrient delivery to those cells. Okay, so back to the squat article. This is just an excellent article because it really bridges the gap between all of the research and the practical application. That's really the type of research that is awesome about HHP because we have a lot of practical application type of research. And so taking the research and determining where the highest muscle activity and forces take place, as we begin to descend into a squat, we can see that shear force as well as shear force on the ACL is very high right in the beginning. That makes sense because remember we're getting that anterior slide. Remember, so if we go back, as we begin to descend into a squat, we're getting that anterior sliding. So this is just another way of saying shear force, because what is a shear force? It's a sliding type force. That's exactly what that represents. So we can see that in the beginning, between about 0 and 60 degrees, color-coded here, we've got lots of anterior type shear force. What I also thought was interesting is the squat isn't considered much of a hamstring exercise, so we usually do other things to address hamstrings. But we do get some activity. Most of that activity happens when the hips are still close to full extension. So between 10 and 70 degrees, right near the top, well before you reach that, we say parallel for a squat, that's where you're getting most of the hamstring activity, but it's still relatively minimal for a squat. Remember the question about why, because the hamstring crosses two joints, and there was a test question on that. Maximum quadricep activity, you're right here in the light blue zone, right here. So if we get less hamstring activity, that allows the quadriceps to better function as a knee extensor. What I also thought was interesting, and people don't realize that the squat can be an excellent way to train your glutes, but you have to get at least down to that parallel point. So we can see from this diagram that the maximum glute activity, so EMG is a way that we measure activity, happens from 90 degrees down below to 135 degrees on that. So in fact, if you're getting insufficient glute activity, that can create problems with the knee joint, because then if the glutes aren't doing their job, what muscle group has to extend the hip? Hamstrings. And why is that bad for the knees during a squat? Because that opposes what the quadriceps are trying to do with the knee. So the best activation strategy is one that we have really strong glutes, so they do their job at the hip. The hamstrings is kind of turned off, and that allows the quadriceps to do their job at the knee joint. And when we're talking about quadriceps, we're not talking about rectus femoris. It's kind of the same deal you have with the hamstring. It's more the vasti muscles that are extending the knee joint. So I also thought it was interesting, maximum compressive forces. So it seems like as you're descending deeper into a squat, you have, you could say, more of your body weight positioned behind the knee joint. So you can imagine if this leg were to flex, eventually it would be down this way with more of your body weight pushing down and back against the knee joint. So you've got compression, as well as in the green area, you hear this posterior shear type force. So part of the reason that you have more compression with a deeper squat angle is due to this wrapping effect. So how do you remember from the article, it discussed that just a little bit. So the combination of your quadriceps and your patella and your patellar tendon kind of creates this rubber band type effect, where if you go into greater knee flexion, we could say this wrapping effect, the quadriceps and the tendon starts to tighten a little bit, so it has greater stiffness. And so the more knee flexion you have, the greater this compressive force into the knee joint. Sometimes I think we tend to include the patella in with the knee joint, but remember, it would be just this compression with between the femur and tibia. So you have compression at the knee joint, but you can also have compression at the patellofemoral joint. So that's the articulation between the femur and the patella. So it went into that just a little bit. I thought this was a really interesting part of the article because it shows that the area of contact for the patella at different parts of knee flexion. So remember, stress is equal to what two things? Force divided by what? Area, right? So the compressive stress on the patellofemoral joint would be affected by how much of the patella, the area of the patella, in contact with the femur. So what you're looking at here is the bottom of the femur. So the femur has a medial and a lateral condyle, and then you have this intertubercular space there. But all of these shapes represent how much contact the patella has with the femur at different knee flexion angles. So if we have a greater area in contact and force stays the same, what happens to stress? A given force, more area means, it means less stress. So that's the patellofemoral joint. So looking at this diagram here, where do we get the least amount of compressive stress on the patellofemoral joint? If force stays the same, but the area is changing, where's the greatest area? And here, can you see how this would represent more area of the patella in contact? So that's lesser amount of compression on the patellofemoral joint. But what's interesting is as you go down a little bit deeper into these deeper squat angles, what happens to that area? It gets smaller, which means what for stress if force stays the same? That means greater amount of stress. So we have to consider if someone has a pre-existing knee issue, we have to know that there's going to be greater amounts of compressive stress on the patellofemoral joint with these deeper squat angles. So that's taking a look at the other side. I don't believe a deep squat causes knee joint degeneration, but if there's already an existing problem, then it's probably best to limit range of motion. I think was kind of the whole point of the article. One of the key points, one of the benefits of doing deep squats was thickening of the cartilage. So remember how it talked about how the body undergoes changes when you're doing those deep squats? The cartilage itself can thicken. It talked about the odd facet on the medial side of the patella. So the cartilage in this part tends to thicken, especially with a deeper type of squat, because this is where it receives the most stress with the deeper squat angle. That was towards about the last paragraph of that article. So our three fundamental stressors, we have compression, we have tension, we have shear. So we have two other types of loads that are more complex. So you can see compression, tension, and shear, but we also have torsion and bending. So when I think of torsion, I think of twisting. Bending, of course, is what you think it is. So let's take a look at the foot, because the foot also has to deal with the force of our bodies. The foot represents a simple anatomical beam. So we have our body weight distributed across the surface of the foot. The supports would represent the heel and also the metatarsophalangeal joints. So again, your body undergoes a lot of stress. If you have one of those jobs where you're on your feet and you're lifting and unloading, loading stuff all day long, how many have ever worked at FedEx or UPS? And my gosh, yeah, on your feet, and that's just, you don't even need a gym membership anymore if you're doing that. But most of the compressive stress here is on the top. So if we're applying a force through here, the tensile stress would be more on the bottom through the dorsal or plantar aspect of the foot. So again, footwear, really important. It's amazing what we put our bodies through. So let's talk about torsion. So you have opposing torques, opposing twisting type forces. A lot of times your spine is in the middle of that. So in this case, and just as a simple example here, we've got the torso turning to the left with the spine in the middle and the pelvis it's hard to visualize this, but the pelvis is isometrically fixed to the right. Is how it would work to maintain balance, because if you have two opposing torques that are acting on the body, they have to be equal or you would lose your balance. So in this case, if I'm turning my torso to the left, I have to have a counter torque acting through the muscles of my pelvis to keep the pelvis isometrically fixed towards the opposite direction. And then I've got my spine in the middle. So that can place a lot of stress on those passive tissues, discs and ligaments. That's why it's important that we have good stabilizing muscles that hold the spinal joints in place. Not saying this is necessarily a poor exercise, it can be, but from my experience and like you had on your lab exam, I prefer more of an approach where we are stabilized isometrically and then we're moving about the shoulders and the hips that way. So really the muscles of the spine were designed to function isometrically, statically. And if we're stable here, then we can move more effectively about shoulders and hips. So movement takes place about joints that are distal or proximal to our center or core, as we say. So torsion can create fractures, spiral fractures. I hope you got a red card and maybe a lifetime ban for something. That looks like it was on purpose, unfortunately. Okay, so we've talked about stress, and now we're going to talk about strain. Okay, so strain. What do you think of when you think of strain? So I can tell psychologically you're probably under a lot of strain and stress, but a week from now it'll all be over, be on to summer. But from a mechanical standpoint, what is strain? Yeah. So if I put a muscle under strain, what am I doing to it? I'm stretching it, right? I'm changing its length. So I'm deforming it in some way due to compression or tension. So we have a formula for strain, and strain is expressed as a percentage. So you take the stretched length, which is going to be greater than the original length. So think of a muscle and a tendon like a rubber band that you're stretching. You take the stretched length minus the original length, and then you divide that by the original length times 100. So you're looking at a certain percentage increase in length. So that's all it is you're just, what percentage increase in length took place. So in order to deform something, you have to have a force. You have to have a stress. So when stress is applied to a body or object, or a material, like bone or muscle, or tendon or cartilage or ligament, when a stress is applied to a material, it undergoes a change in length. It deforms, it undergoes strain. So the strain would be expressed as a percent of the original length. So Dr. Bain talked about the stress-strain relationship a little bit. I like the way that he presented this concept because he talked about the Goldilocks zone. I don't know how he came up with that, the Goldilocks zone. What does the Goldilocks zone mean? What did Dr. Bain mean by the Goldilocks zone?
Not too stiff, not too pliant, just right.
Yeah, thanks, Joe. That's a great way of explaining it. So for just a recreational exerciser, why is the Goldilocks zone important? What's the health benefit? Where Joe said not too tight, so that's good, right? Because we don't want too much stress on our joints. So the tighter the muscles are, there's more stress on the joint. But what else? If we're a recreational exerciser, we want to go out and jog and be efficient in our running technique, why would we want something that's a little more, with more stiffness, we could say?
More force.
Yes. So how many remember the stretch, shorten cycle? Okay, so we want an efficient return of energy. So going back to what Joe said, we want a musculotendinous unit that is compliant enough to take the stress off of our joints, and it won't hamper our stride length, because remember, stride length is dependent a little bit on flexibility. But we also want something with enough stiffness for an efficient energy return. So stride efficiency is one of the, if you've studied distance running, think of how important stride efficiency is. And more research is showing that it's not really the difference in VO2 max or anaerobic threshold between distance runners. What really matters is efficiency. And so now they have all these fancy shoes. Had a student give a presentation on carbon plated shoes and how it makes athletes more efficient. So the stress-strain relationship is expressed as this unitless ratio. So this elastic modulus. We take the amount of stress divided by the amount of strain. So this elastic modulus represents the slope of the stress-strain curve. So for a given amount of stress, if these two lines represent two different materials, okay, we can apply the same amount of stress and a stiffer material won't undergo as much strain. Whereas a more compliant material for the same amount of stress will undergo more strain. So the elastic modulus would be much less for a compliant material versus a stiff material. So the elastic modulus would be a lot more for a stiff material, because for a given amount of stress, we're undergoing less strain or less change in shape. Does that make sense, everybody? Okay. So The stress strain curve can be dependent on how the force is applied, the duration of force application. Under small loads, an object might be more elastic. So from a mechanical standpoint, we need to understand what the definition of elasticity is. Elasticity means that when the load is removed, that object will return to its original shape and dimensions. So we stretch a material like a rubber band, and if you let go of the rubber band, what does the rubber band do? It goes back to its original shape. So that's what being elastic means. Material can also get to the point where it undergoes a permanent deformation. So if a load is large enough or applied for a long enough period of time, that material will stay at that shape. So permanent deformation, that would be plastic behavior. So the point in the stress strain curve where if we apply additional stress, the material stays at that length is called the yield point, sometimes called the elastic limit or proportional limit. So think about ligaments. How many remember the shoulder separation video that we watched with the football player on Tuesday? Remember the part where they talked about the healing process and the ligaments were kind of stretched out? Ligaments can exhibit some of that behavior where they never, over time with healing, they never go back to their original length. So an athlete can have a little bit less joint stability because their ligaments have been permanently changed as a result of that injury. So we take this material, and this would be the elastic region. So as stress is applied in the elastic region, if we remove that stress, it's going to go back to its original length. If we go beyond this, if we apply more stress beyond that yield point, it's in the plastic region. So that's the limit where we'd have some permanent change or permanent deformation. So this is an important definition. This is one that I'll ask you on the final, so you want to key into this one. So anisotropic, so means that tissues have different characteristics in terms of their stress-strain relationship based on the direction of the force. So for example, this is a tendon. Okay, tendons attach muscles to bones. Tendons are much stronger and they exhibit more stiffness with tensile loads. Okay, so muscles will pull on tendons that are anchored to an attachment point on bones. So we say tendons are stronger with tensile stress that is applied along the axis of a tendon, parallel to the axis of a tendon. Whereas tendons are weaker dealing with shear type stress. So shear type stress would be perpendicular to the tendon in this direction. So it would be against how the fibers of the tendon are aligned. So I had you read or watch the Dr. Bain video. So in terms of stretching, when do we tend to notice a decline in force and power? What duration of stretching are we first starting to notice a decrement in force and power? It was kind of a dose-response relationship. Remember how he put that graph up there? It was about sometime between, it was about 14 minutes into the presentation, maybe a little less than that. He put that graph up there and it kind of looked like a dose response for a different duration. So you had less than or equal to 30 seconds, and then you had 30 to 60 seconds, then you had 90 seconds. And it appeared that the greatest decrease in force and power was at or greater than 90 seconds. But the question was, when do we first start to notice? What duration of static stretching do we first start to notice a drop? It was about 30 seconds, less than or equal to 30 seconds was when we first start to notice. And then when you get up to 90 seconds, then you're really starting to notice. What percentage was the drop in force and power according to his literature review? It was about 5%. So then he brought up a review from some Australian researchers that was around 7%. So it's kind of in that ballpark. So an elite athlete, that is significant, right? So elite athletes, what was his analogy? Are like what? Ferraris. So Annalise is a Ferrari. And Pocatella this weekend, be a Ferrari. So we want tighter tendons, right? Because we want that quick reactive response to the ground, okay? But all the rest of us, that health and fitness, the Goldilocks zone becomes important, where we want to take some of that stress off of our joints, but we also want an efficient return of energy. So when's the most appropriate time to stretch then if you're working on mobility and stuff? So when would be the best time then? If you're concerned about that 5 to 7%, then maybe you want to do something more dynamic before your event, but maybe more, post-exercise would be appropriate. He also talked a lot about muscle spindles in there. Muscle spindles respond to how fast a muscle's being stretched, but also how much. Do you remember the two sensory parts of a muscle spindle? So the bag fibers, nuclear bag fibers in a spindle, remember, respond to the rate of stretch, so how fast. Whereas the nuclear chain fibers respond to how much of a stretch. So what is the response? What does a muscle spindle elicit? A contraction, yeah. So muscle has a certain capacity to stretch. Muscle can stretch to about 50% above its resting length. So we still get muscle pull when muscle is stretched too much, too rapidly. But muscles, in contrast to tendons and ligaments, have a greater capacity to undergo strain before we get this trauma that you see here with this back strain. So this muscle pull looks like the distal part of the trapezius there, where it attaches down here to the spine. Okay, so I want to talk just a little bit about each type of tissue, and then we're getting down towards the end, so almost there. I have a good video here on cartilage as well. So bones support compression. They're strongest in resisting compression. Tension is after that, and they're weakest in resisting shear force. I want you to notice that when we talk about bones, tendons, ligaments, and cartilage, there are 3 components that they all have in common. So they have differing amounts of water, they have differing amounts of collagen, and they also have different amounts of ground substance. So I was reading up on ground substance as I was going over this lecture, and the analogy that I came up with is ground substance is like glue. So it holds the collagen and cells together. It's kind of a pulpy type substance. So bones are only about half mineral. The rest of bone is alive with organic type material. Bones are always remodeling themselves. So remember on Tuesday, from the video, every 7 years, a healthy adult will replace all their bone cells. So the high mineral content gives bone compressive strength, whereas the high collagen content gives bone its tensile strength. So bones are able to bend. What was the something law? What law illustrates the adaptation of bone to stress? The specific adaptation of bone and as well as other tissue. Remember the guy? Good test question. It's Wolff's Law. Just remember Wolff's Law from around the first part of the presentation. So cartilage. Okay, cartilage is a type of connective tissue. We have different types of cartilage in the body. So hyaline or articular cartilage at the ends of bones. We also have fibrocartilage. Can you think of any examples of fibrocartilage? Yes. Yeah, thank you, Logan. Good. So the discs, the intervertebral discs, we have another disc, the symphysis pubis, as well as the attachment of the ribs to the sternum is, they are fibrocartilage. Elastic cartilage. Yeah, so your ears, and Logan's giving me all the answers over there. The ears and your nose are examples of elastic cartilage. So again, look at the composition: collagen, water, and ground substance. Cartilage has more collagen and water versus bone. Human articular cartilage is amazing. So it's 1 to 3 millimeters in thickness. It has a role in transmission of force between articulating bones. But again, it relies on interstitial fluid to supply oxygen and glucose to meet its metabolic needs and to maintain itself. So I have just this little presentation here on cartilage, so we'll watch that now. This is from that same series, Human Body Pushing the Limits.
We carry awe-inspiring strength in our muscles that we can summon when we're pushed to the limits. But every day, every hour, our bones have to handle huge forces. They take a hammering from normal life. To survive, the human skeleton has evolved a material so strong that no technology can match it. These streamer discs are among the world leaders at freerunning, a sport that tests the body's flexibility to its limits. And it's only possible because our legs have high-performance shock absorbers. Running puts a strain on our legs 3 times our body weight. A jump can put the skeleton under stress equal to 10 times the body weight. But the body has ways to handle such forces. On lending, leg muscles absorb energy, like giant elastic bands, so we don't simply collapse. The real key to withstanding shock is human engineering that modern technology can't match. Our knees. The knee bones are connected by ligaments, lengths of fibrous tissue that crisscross. As the joint flexes, they stretch. But ligaments are twice as tough as nylon rope, with a combined breaking strain of nearly a ton. At the joint's core, between the 2 bones, is a remarkable material. Cartilage, a mere fraction absorbs the impact's full force. Cartilage shapes the nose and ears and is made of collagen. But in our joints, cartilage has remarkable properties. A weave of collagen fibers is surrounded by 80% water. On impact, it acts like a water-filled cushion. Knee cartilage is so strong, it can bear 7 tons before it gives way. What's more, on the pad's surface, collagen fibers are uniquely arranged to make it almost frictionless. The knee bones roll over one another like well-oiled bearings. In a lifetime, hundreds of millions of shocks pass through this tiny area, a uniquely durable design.
Okay. You notice we absorb 10 times our body weight, up to 10 times our body weight on a jump. I liked how they compared the cartilage to shock absorbers. They also talked a little bit about tendons and ligaments in there. Ligaments are a little bit more elastic, so they have a little more give versus tendons. Tendons is in the presentation, they're like nylon ropes, but a lot stronger. So ligaments have the addition of this elastin. So elastin, studying that before this lecture, it's like a rubbery protein. So it allows the ligaments to give a little bit, which if a ligament is giving just a little bit, remember our discussion on impact, force applied over a period of time, you're going to get less force if a ligament is able to distribute that force over a longer period of time versus all at once. So that's important that they have this elastin. The major difference between cartilage, ligaments, and tendons has to do with collagen. So in collagen, there's a random arrangement. Or in cartilage, there's a random arrangement of collagen. So that was in the video, the random crisscross pattern of those collagen fibers, whereas in tendons and ligaments, it's parallel. So as tendons and ligaments get stronger and thicker, they're adding more bundles of collagen. So that's important as muscles get stronger as well. So in terms of the behavior of tendons, especially, as we apply a force over long duration slowly in a tendon, we get this response. There's another mechanical term. So as a tendon undergoes a certain amount of stress, slowly over time, it will start to creep in terms of its strain. So it will slowly start to get longer. If that stress is applied all at once at a very high rate, tendons exhibit greater stiffness with less change in length. So as I was reading that, I thought about how that applies to stretching. So as we're doing a traditional static type stretch, how is it that we want to engage the stretch? It's a slow process over time. We go out to a certain distance and we hold for a period of time, and then we notice that after a period of time, you notice the muscle starts to relax a little bit, and we go just a little bit further and hold. So that's this creep mechanical type of response to stretching. So that's the end of chapter 9. I want to make sure, is there any questions at this point? At your study guide. So those of you that weren't able to get the assignment to me, make sure you can do it. Just send it to me through email or drop it off. Okay, thanks for a great semester, and a few of you need to finish the lab finals. I'll see you in just a minute. It's in the assignment folder.
I have it.
Oh, okay. Yeah,
I tried to do that in my AP, you guys will, it's too hard.
I would have done the same thing.
So,
So, oh yeah, just anytime.
all right, thank you. Look for
So that's the patellofemoral joint. So if you can imagine the quadriceps running past the patella down to the tibial tuberosity, it's kind of like a rubber band. So as you squat, you're stretching that rubber band. So if that rubber band is running all the way through here, it's gonna have more tension in it, which is gonna push into the joint more. So it's like if you took a rubber band and wrapped it around something and you increase the stretch in that rubber band, anything that it's pushing against is going to have more force against it because it's tighter. And that's what happens when you squat.
Okay, and
That's the wrapping effect. So the wrap is the quadriceps going all the way down to here. So it wraps around the knee joint. It's a muscle and a tendon wrapping.
okay. Okay, I'll write this down.
Is it doing better than it was?
Better than it was.
You know how mine got better?